I'm Harshit and I work with Professor Rama. And I'll be, so first of all, I would like to thank the organizers for this opportunity. And I'm going to be talking about a work that I did with Professor Rama, which is titled Fluttering Without Wind, Stokesian Quasi-Periodic Settling. The main theme of this talk is that overdamped limit is not as uneventful as it seems. Viscous forces are known to damp out relative motion between bodies and fluid. And one would expect motion as complicated as fluttering of falling leaves to occur when inertial forces are much more significant than the viscous forces. The ratio of inertial forces to the viscous forces is given by Reynolds number. So here's an image which shows an experiment performed by Belmonte et al., in which what they did is they took a metal strip and let it fall in a fluid at high Reynolds number. And what they observed is that this metal strip flutters as it falls, leaving behind these nice trailing vortices. Now, if you compare this with the overdamped limit where Reynolds is 0, this is a viscous dominated regime, and you do not see any wake structure behind falling objects such as an ellipsoid. In fact, when you look at the motion of falling ellipsoids, it simply maintains its orientation in the overdamped limit and it does not rotate at all. But ellipsoids have more symmetries. They have 3 planes of symmetries. If you consider an object which is less symmetric than an ellipsoid, for example, an object which has only 2 planes of symmetry, it turns out that its motion can rotate as it falls, and its motion can be as complicated as falling leaves, for example. So the goal of this work is to characterize the range of dynamics that can occur when we consider bodies with only 2 planes of symmetries falling in viscous fluid. In the viscous dominated regime, the forces and torques that act on a body are linearly proportional to the linear and angular velocity of the body. And the proportionality constant is what's called the resistance tensor, which only depends on the geometry and the size of the body. The coupling tensor B leads to translation rotation coupling, so if a body is falling in a fluid, it's the B tensor which makes it rotate as it falls. Geometric symmetries of the bodies can be used to simplify the structure of this resistance tensor. For example, for a sphere, we have a very simplified structure of this resistance tensor, in which case the A and C matrices are just proportional to identity, and you have no coupling at all. So a sphere falling in a viscous fluid will simply fall down and not rotate at all. So also, this is also true for bodies with 3 planes of symmetries. As we saw for ellipsoids, we do not have any coupling at all. The B tensor is 0. But if you consider bodies with 2 planes of symmetries, for example, a body like this, we can use symmetry arguments to reduce the structure of the full resistance tensor. For example, we have 2 reflection symmetries here, P3 going to minus P3 and P1 going to minus P1, in which case we can use these symmetries to reduce the structure to this form, where we have non-zero coupling between rotation and translation. And when you consider this type of body falling in fluid, you have force acting on the fluid, acting on the body, which is the force due to gravity, and there is no torque acting on the body. And even though there is no external torque acting on the body, you can have non-zero angular velocity just because this coupling tensor is non-zero. As I said before, this work characterizes the range of sedimentation dynamics exhibited by bodies with only 2 planes of symmetries. The most convenient dynamical variables that can be used to describe the motion, the rotational dynamics of such bodies, are the vertical and horizontal projection of the body fixed coordinate axis. X, Y, Z are the lap fixed coordinate axis, and P1, P2, P3 are the body fixed coordinate axis, which keep on changing with time. To characterize the dynamics of such a body, we look at the vertical projections of the body fixed coordinate systems denoted by Py vector here. It turns out that this vertical projections of the body axis are decoupled from the horizontal projections, which I'll come to in a minute. And you can write down a 3-dimensional dynamical system for these vertical projections of the body axis. And there is a constraint that says that the Py vector has to be a unit vector. So the phase space of this dynamical system lives on a sphere. There are parameters alpha p and alpha r which are proportional to the coupling coefficients and only depend on the shape of the body. So alpha p and alpha r will occur throughout the slides, and I just want you to remember that these two parameters only depends on the coupling. Yeah, they are proportional to B31 and B13, two factors. So based on the sign of alpha p times alpha r, which depend on the shape of the bodies, we can classify the bodies based on their rotational dynamics. First case is when the product is negative, which we term as settlers, in which case the bodies asymptotically reach a stable orientation as it falls, in which case one of the body fixed coordinate axes lies parallel to gravity, and it keeps on falling like this, maintaining its orientation. The second case is drifters, for which this product is zero, in which case they again tend to go towards its stable orientation, but in this case the body axis may not lie parallel to the gravity. And in this case they keep on drifting horizontally while settling, just as we saw in the case of ellipsoids. The third and the most interesting case are flutterers, for which this product is positive, in which case they keep on rotating as they fall, and they can even perform periodic as well as quasi-periodic orbits. And they also show some intricate patterns in the horizontal plane as they fall. So to understand the dynamics of flutterers, so dynamics of drifters and settlers are somewhat trivial, but to understand the dynamics of flutterers, we first look at the py dynamical system, which are the vertical projections of the body axis. It turns out that there is a conserved quantity in the dynamics of py, which is given by this quantity here. This is a phase space of flutterers, a phase space of py dynamics, which lives on a sphere. It turns out that for flutterers, we have two saddle fixed points, one denoted by this red dot here and other lies on the other side. And then there are four center fixed points about which are denoted by black dots. And these closed loops are the h equals to constant curves in which the trajectories of py dynamics live. So if you start at any point here, it would keep on going on these closed orbits, indicating periodic orbits in the py dynamics. The maximum value of this conserved quantity h occurs at the center fixed points, while the minimum value, which is 0, occurs at these red great circles which join the two saddle points. If you look at the time period of the py trajectories, how it depends on the conserved quantity, it turns out that as h goes to 0, as we go from the center fixed point towards the saddle points, the time period increases unboundedly, because the closed orbits get closer and closer to the saddle points, and which is why the dynamics near the saddle point is very slow, and which is why the time period starts to grow unboundedly. Now, having characterized the dynamics of py dynamical system, the remaining part is the dynamics of, having characterized the dynamics of py dynamical system, we are left with the other part of the dynamics, which is given by the horizontal projections of the body fixed axis. The horizontal projections are denoted by px vector here. And it turns out that this dynamics is also quite simple. It's simply a non-autonomous linear system which is driven by the py dynamics. This A matrix is time dependent, and it is dependent on the py dynamics. So if py dynamics is time periodic, that implies that this A matrix is also time periodic. And this is a classical problem in flow K theory. What we have is that vertical projections are periodic in nature, and they drive the horizontal projections periodically. Now, flow K theory shows that the solution to the px dynamics can be separated into two parts. One oscillates in time with the frequency nu, which we call driving frequency, and another part is also time periodic, which oscillates with the driving frequency. And it is the ratio of these response frequency to the driving frequency which determines the nature of dynamics. If the ratio is rational number, you get periodic orbits, and if the ratio is irrational number, you get quasi-periodicity. Is the dependence of the ratio on the conserved quantity, and it seems numerics suggests that this ratio is bounded between two values and it varies continuously, indicating dense existence of quasi-periodic as well as periodic orbits. I won't be explaining this part, but it just shows two instances One is the periodic and another is quasi-periodic. In periodic case, the px dynamics form closed loops, while in the quasi-periodic case, it spans some region on the sphere. And correspondingly, you have nice patterns forming in the horizontal plane as the body falls. I'll just say that we can construct all these classes of bodies, 3 classes that I discussed, by just bending a spheroid and making its cross-section concave or convex. The parameters alpha p times alpha r, they depend on, this is how they depend on these 2 a and b parameters. And if, for a given b, for a given concavity, if we keep on increasing the bending parameter, we go from flutterers back to drifters to the negative part, which is settlers. Okay, so I'll end with this. Here are some take-home messages. That translation-rotation coupling leads to rotation of bodies during sedimentation, even in the overdamped limit, and then the body can show intricate patterns and complicated motion. Bodies with only 2 planes of symmetries can range from settlers to drifters to flutterers based on their rotational dynamics. This is how we have classified the 3 types of bodies. And all 3 classes of bodies can be obtained by bending a spheroid and making its cross-section concave or convex. So I'll end with this. For more information, you can look at this article here. Thank you.
Questions?
This system, do you ever get chaos?
No, we do not have chaos. We at most have quasi-periodicity. But
why is that? Because in principle you have like 6 degrees, right? And so
we do have 6 degrees, but the way dynamical system is, we have a periodic part in 3 dynamical variables, and then another part which is just driven periodically by the periodic part. And at most it can do is just quasi-periodic.
But if you make it even more asymmetric, then you
then yeah, if we just consider, let's say, 1 plane of symmetry, bodies with 1 plane of symmetry, then we expect it to be chaotic.
More questions? If not, let's thank Harshit for his talk.